In this video you will learn how to derive the two forms of the current divider rule from the voltage equality in parallel circuits in combination with Ohm's law. And by the end of this video you will know three formulas that you can use to calculate unknown currents in a circuit depending on the given and sought after quantities. And finally, as always, there's going to be a summary of the most important facts from the video at the end for you, so stay tuned. And my name is Andreas from The Fearless Engineer, and here we go. Now, before we dive into the actual derivation of the current divider rule, let's quickly recap what we have learned in the previous video in case you have watched it on the use of the current divider. What you can see here is a branched circuit. We have a power source, a voltage source to be exact, on the left side, which provides the circuit here with a steady current flow. The current arrives here at this junction point and then splits up into a left part and a right part. The left part has a resistor with a value of 100 ohms. The right part has a resistor of 400 ohms. And as you can see when I run the video, that the amount of current running through the leftmost resistor is much larger than the amount of current running through the rightmost resistor. And we have already seen that depending on which quantities are sought or known, be it I1, I2 or I total, a different form of the current divider a different shape of the equation, so to speak, must be chosen. We have already looked at the equations, but in this video we will derive these equations from scratch using some key concepts of electrical engineering. Now, what you can see here on the right side is this sub part of the circuit, which is concerned with splitting up of current. You have a total current entering the top node. Then this splits up into the left branch with R1. The current is called I1. This is what we're looking for. R1 is given to us in this variant, and also the total amount of current is given to us. We also know the resistance value in the second branch, but we are not aware of the current flow in this second branch. So we do not know I2. Now, this form is what we are going for right now, and on the next slide we will derive the formula to do so. The first concept we're going to exploit is the voltage equality with a parallel connection, which states that the total amount of current U total, which is the source voltage, is identical to the voltage dropping across all these various components here, and we are now interested in the voltage across R1. And as you might recall from the video on voltage and potential, voltage is nothing more than the difference between two potentials. So we have a potential at this topmost node here, and we have another potential at this bottommost node there. And as this node has the same potential for these two components as well as for the power source, all the voltages are arranged in parallel and they are identical to each other, which allows us to make this assumption here. The second is to then eliminate the voltage by applying Ohm's law. We are simply replacing the voltages by the product of resistance and current flow, which we can do for the left side and also for the right side. Now we have to come up with a solution for the total resistance, which can be arrived if you have watched the video on how to compute the total resistance of a parallel setup. Which can be arrived by multiplying the two resistance values R1 and R2 and dividing them by their sum, which basically is the same as adding up the inverse resistance values, 1 divided by R1 plus 1 divided by R2, and then taking the inverse of the sum. This is what yields this expression here. And if you replace R total with this expression there, then you are almost all the way there, because what you're looking for is I1. You have R1 given, R2 given, I total given. So basically now you have all the values you are looking for, or you have the value you are looking for, and all parameters are known to you. So the only thing left to do is to divide by R2 on both sides of the equation, which is what we're going to do on the next slide. And on this slide here, you can see the variant 1 of the current divider rule. I have solved the equation for I1 on the left side, and I have solved it for I2 on the right side. So if you're looking for I1, you simply need to multiply the total amount of current entering the node with the fraction or the ratio between R2, which is the resistor in the opposite branch, and the sum of the two resistors, R1 plus R2. If you are looking for I2, you have to take the same total amount of current and multiply it with R1, which is the resistor in the opposite branch, where I2 does not flow, and divide it also by the ratio or by the sum of R1 plus R2. So these two variants can be used when you have the total amount of current as well as the two resistor values. And the second variant, we do not have the total amount of current given, but we have the partial current in the opposite branch, and we are still looking for I1. So for this configuration, we also want to have a formula which helps us compute the missing current I1 here. And we can derive it in the exact same way as before. We are exploiting the voltage equality between these potentials here, the topmost potential and the bottommost potential. And now we are simply equating the current, the voltage drop across R1 and the voltage drop across R2, which states that U1 equals U2. And by applying Ohm's law again and entering the product of resistance value and current, R1 times I1 equals R2 times I2. We get this simple form here, and we can simply solve it for I1, which yields this second variant of the current divider rule, which states that the current through the first branch is identical to the current through the second branch multiplied with the ratio of the resistance in the second branch divided by the resistance value in the first branch. So this is another variant which you can use depending on the parameters which are given to you. Now let's quickly summarize the most important takeaways in this video for you. First is, depending on which quantities are sought after or are known, a different form of the current divider rule must be chosen. And then both current divider rules, which we have seen here, they can be derived from the voltage equality of parallel resistors and from Ohm's law. And in general, the currents through parallel branches, they divide in the ratio of the reciprocal of the respective resistance values. And lastly, alternatively, Kirchhoff's first rule can be used to express unknown currents by known quantities as an additional tool which you can use. That's all from me for now today. If you have any questions regarding the current divider rule, leave a comment down below. Also, if you have suggestions for future videos, leave them here. And I wish you a nice day now. See you next time here on The Fearless Engineer.